So welcome back, children. In the previous video we talked about inductance and mutual inductance. This video we will talk about self-inductance. Let me start with a scenario. Suppose you have a loop. Of conductor. I'm going to have a magnetic field produced by another loop where you have current flowing through. So clearly this will have field. So showing like that. So field direction will be something like this. So there is this field from this loop, magnetic field that goes into this loop. And if this current changes, then clearly an EMF is going to be generated because the flux through this will also change because the current in this loop changes. Okay? Now, I have another loop. So, when this changes, when the current in this loop changes, the flux is going to change in this loop and also in this loop. So, a current, say small I1 would be flowing through this loop and another current, maybe I2, could be flowing in that loop. You see, because the current I2 is flowing in this loop, then this will set up a field, this will have its own field, and that field would be something like this. Okay, same. So it's going like that. So this field also will be like this. Notice now that this original loop is going to be affected by this loop and also this loop. But even though this is the loop which is producing the original magnetic field and thus causing the currents to flow, but the moment there is a current elsewhere, then there is going to be a magnetic field due to this loop also in this loop. So, if both the currents change for some reason or the other, then clearly the current in this loop will be affected by now both I and that's I2. So what if I combine these two loops now? Now I'm going to have a coil like this. Okay, I combine these two loops and likewise I have a few more loops. And what will happen now? So then there will be a current, let's say small I, flowing through this, and it will make one loop and another loop. So you notice that this loop will produce a magnetic field and this loop also will produce a magnetic field and this loop also will produce a magnetic field. And if I varies, take this loop for example. This will be affected by the magnetic field from this loop and this loop and this loop. Because the current is varying, it's the same current, but the current is varying in all these loops, then one would be affected by the other. Because the magnetic field in this particular loop, in this one loop, is now not dependent on only this loop alone. Now it will have a combination of this and this and this and all the other loops which produces magnetic field. So the total magnetic field in one loop will be not exclusively from this loop, but from all the other loops too. So if this current varies, then in other loops also that current will vary, because the same current. If currents in other loops vary, then flux is going to vary, and if flux varies, then the flux which is going through the original loop will also vary, and that will produce an EMF. So if the current in its own loop, the same coil, if that varies, then there will be an EMF generated, because the magnetic field anyway varies. Magnetic field through that loop varies. It is not just for that loop. Even if you take a small bit of this, or this, or this, and this bit is going to be impacted by this, because you notice that this is in the magnetic field produced by this bit too, and this bit too. But even in a single loop, then a very small current element will be affected by another current element. So, on the whole, the current which is flowing through one coil will affect itself, and this is what we call as self-inductance. So the change in the current which is flowing through the coil will produce its own EMF, which we call as a back EMF. We call it as a back EMF. Because the current flowing through the coil changes, then the flux that is linking the loops change. So clearly, there will be an induced EMF in that setup, and that EMF is called as back EMF. So this inductance is called as self-inductance. So likewise, we can come up with an expression for self-inductance. Just as we came up with an expression for mutual inductance, we can come up with an expression for self-inductance. Again, it depends on the flux, right? So the flux phi of this coil phi B is proportional to the current, say I, flowing through that coil. Then the total flux linkage will be N phi B. Right? Each coil will have flux linkage. So N phi by phi B is proportional to the current which is flowing through this. Phi B is proportional to current, N phi B is also proportional to the current. And if I'm going to use a constant of proportionality, then it will be L into I. And this L is called as self-inductance. The idea is that a coil will not be affected only by field from another coil or another magnet. It can be affected by the field produced by its own current. And that is self-inductance. This is what I want you to understand. So this is N phi B is equal to Li. Okay? Then what's the EMF induced? So EMF is going to be equal to minus N d phi d by dt, which will be equal to say minus L into di by dt. Okay, so now let's find out the value of L. Okay, let's take L di by dt is equal to N d phi b by dt. But what is phi b? Well, phi b will be, okay, let me come up with this. Suppose I have B, magnetic field is B. From our long solenoid equation, I can say that B is equal to mu naught N into I. This we know. If this is a long solenoid, then B within that solenoid can be given by this expression mu naught n into I. Okay? So then what is the flex? So that would be B into A, area of the solenoid, area of that circle, that one loop. That multiplied by B, the magnetic field strength, will give you the flex to that, the phi value. So that is going to be equal to N and keep like that. And this will be B into A. So B is mu naught, let's say, D. B is mu naught Ni, which is B, to area is phi. Suppose that this is the radius, R is the radius of the coil. So pi R squared divided by dt. Well, out of this we can see that mu naught is a constant. What is N? N is the number of turns per length, unit length, right? The number of turns per unit length. And I is a current flowing through it. And pi R squared, pi is a constant, R radius also is a constant, N is a constant, mu naught is a constant. And there is only one variable there, and that is actually I, di by dt. Okay. So this will give me N mu naught small n pi R squared multiplied by di by dt. But so I have this di by dt into here. So L must be this, because di by dt I have got here. So this must be my L. So my self-inductance L must be equal to N mu naught N pi R squared. And what is N? N is the total number of turns. So that is nothing but N times the length. Suppose if this is the length of the coil, let's say, then NL is equal to the total number of turns. So then if you put that also there, then I'll take mu naught out, mu naught, and NL into N, it's going to be N squared L pi R squared. Okay. Usually, like you take all these unchanged constants out first and write it. So it's going to be L is equal to mu naught pi into maybe N squared L R squared pi R squared N squared L. So this is the self-inductance of the coil. And what did we have for mutual inductance? For mutual inductance, we had this expression. Okay, mutual inductance was this. Mu naught and pi, then R1 squared, then N1, N2 to N. Okay? So you can see that they are similar. The only difference between mutual inductance and the mutual self-inductance in this case, particularly the coaxial case, is that mu naught pi R1 squared, they are matched, and instead of N squared you got N1 multiplied by N2, and then L will be essentially. You'll be able to remember this formula very easily. So that's why I just wrote the mutual inductance formula along with the self-inductance formula. But notice that this mutual inductance M is for that specific case of having two coaxial solenoids. It would not be the same for all the other cases. In that case, this is what you got. Okay. For another case, it could be different. M, the mutual inductance. But L, the self-inductance for a coil, can be given like this. This is self-inductance and this is a mutual inductance. In both cases, we have not considered any medium. We always, it was assumed that we were in vacuum. Suppose if you have a medium, okay, suppose like I have 9 P's, between these two loops. So for example, like even here, I may have 9 P's, like that, can have 9 P's. So now, I need to consider the permeability of this also, because magnetic field is going to be multiplied. You are going to have no longer B, you are going to have a much bigger magnetic field. So it's not going to be mu naught Ni, but it will be mu naught mu R into Ni. Same thing holds good for the mutual inductance too. If you are going to have a medium around which you have wound this coil, then the permeability of that medium should also be considered when you write this equation. In that case, with a medium, let's say with a medium of permeability mu, mu naught mu R, right? So that's the permeability mu is equal to mu. Then instead of mu naught, you need to put mu naught. Instead of mu naught, you have to put mu. So then mu naught will become mu naught mu R. So in that case, your L is going to be mu naught mu R, then pi, say R squared N squared L. Or for M, in that case is going to be equal to mu naught mu R pi R1 squared N1 N2 to N. Okay. So you can see that both the self-inductance and the mutual inductance depend on the geometry of the coil and the permeability of the medium around which the coil is wound, not the material with which the coil is made. Okay, it's the same for say an aluminium coil or a copper coil. It doesn't depend on the material; it depends on the geometry. But if you put say an iron core and around which you are winding this, in that case, the mu will be the mu of the iron core. It has nothing to do with the coil. Okay, I can use aluminum, I can use silver, I can use copper, I can use anything, but the inductance will not change because of the material I use. But it will depend on the core. As long as the geometry remains the same, both aluminum and copper and other things will give you the same inductance, provided the self-inductance and the mutual inductance. So what will change that is the core, the type of core you have. So when I talk about permeability, I talk about the core, not the material with which I make the wire. You have to keep that in mind. For aluminum too, if you have these dimensions, L is the same as that of copper. If copper has the same dimensions, it will have the same L value as aluminum will, or any other thing, silver, gold, doesn't matter. It depends on the geometry. And then when I talk about the medium, then I talk about the core I insert. If it is iron, doesn't matter whether you have an aluminum coil or a copper coil, the inductance will be the same. You have to keep that in mind. That's why I'm stressing it so much. Hope this is clear to you. So now that you have seen what self-inductance is, we will go on to do some other derivation based on work done and the power considerations. Okay. So what is electric power? Electric power P is equal to V multiplied by I, the voltage multiplied by current. So in this case, P is equal to the induced EMF E, or epsilon, okay, multiplied by current I at any instant, at any point in time. P is given by epsilon multiplied by I, E into I. We will keep it simple. What is power? Power is the rate at which the work is done. So P is dW by dt. The rate of change of work is power. So here, this is equal to, I'll take I out first. Then what is E? The EMF induced, we know this. The EMF induced magnitude, we just take the magnitude, is equal to N d phi B by dt, and that is also equal to L di by dt. So we just did this. I'm going to put L di by dt here. L di by dt here. Okay. So now I can cancel this. So my dW is equal to L into I di. See, if I have a circuit like this, I have a coil, and then let's say I have battery or something, and notice that I have a switch. The switch is open now. So initially the current is 0, and if I close the switch, then the current will change from 0 to some value. Say a constant value could be I. Let's say that I will start from 0, now it has reached current value I. So this current, the maximum current, I'll say this is I. So the current I has gone from 0 to I. Okay. So this is what has happened. So now what will happen to this expression? So if I integrate this, now what is the work done in I going from 0 to a particular value, capital I. So that is going to be equal to, work done is equal to the integral of 0 to capital I and L I di. So this will be the total work done in taking the current from 0 to capital I. Because you notice that there will be back EMF, there will be, the flux will start changing, and then that change will be resisted by the coil. So you have to do work against it to push more and more current into it. Okay, where there is a back EMF coming. When you are trying to put this current, this voltage there, then there is a back EMF coming from it. Okay, so this W is equal to, say, 0 to I, but now L I can take out, it is a constant, okay, because it depends on geometry and the permeability of the medium, the core. So I can take that out. That has nothing to do with the current, right? So I can take that out. Then I got I di. So this will give me L I squared by 2 I di will give me that. So then I have these limits 0 to I, and that will give me L I squared by 2 minus 0. If I put 0 in place of small I, and then become 0. So the work done is equal to half L I squared. See, what it tells you is that in the circuit, when I close the switch, and I have to, this battery will have to do work to push current into it. Because there is a back EMF coming, it is going to resist this battery from sending the current into the coil. So that's a back EMF. So the battery does work against it. suppose I've gone from 0 to say 2 amperes, and let us suppose that this inductance is 1 Henry, example. So you've got 1 Henry inductance, self-inductance here, and then you have raised the current from 0 to say 2 amperes. Then what is the work you have done? What is the energy you have expended to set up this magnetic field? That would be half into, for L, I said it's 1, and for I, 2 square, 4 by 2, 2. So 2 joules of work the battery has to do to take the current from 0 to I. So that energy is stored in the magnetic field, because as I goes, like I is flowing, now there's a magnetic field, you notice. Okay, that's a magnetic field. If there's a magnetic field, current goes like that, then notice that the field is going to be set up like this. Okay, so it's going to be stored in that magnetic field. The energy has to come from the battery. Okay. And I also want you to compare the kinetic energy equation. If you see, if you take kinetic energy, what's the equation you get? It is equal to half mv squared. You see, there is some kind of a similarity between this equation and this equation. You have an half, you have an half here. And for L, you have m. For I, you have v. So what does it mean? So what does this do in the normal sense, in mechanics? What does mass do? If you are trying to push something, if you are trying to increase the velocity of it, then the mass will try to resist it, right? You give a certain, you apply a certain amount of force. The bigger the mass, then smaller the acceleration, because mass will try to resist the change. Okay, that's a measure of inertia in mechanics. Mass is a measure of inertia in mechanics. So mass will work against velocity. It will try to resist the velocity. If you try to push it and say, no, I just want to go like this, I don't want to increase, then you really need to push it to increase its velocity. So mass is a measure of inertia in mechanics. So likewise, look here. If I try to increase the current, what's going to resist? The inductance, the self-inductance of the coil. It will say, no, don't change the flux, don't change the flux, don't increase the current. If you increase the current, flux is going to change. I don't want that change to happen. Okay? I just leave me alone. It's that kind of a cry you get from the self-inductance. So you can say that self-inductance in electricity and magnetism is equivalent to mass in mechanics. Mass resists increase in velocity. Self-inductance resists increase in current. Okay? So this is the mass equivalent. L, the self-inductance is the mass equivalent in electricity and magnetism. Hope this is clear to you. Okay, we've talked about both self-inductance and mutual inductance, and even inducing EMF with a magnet and stuff. Let's try to put all these things together to understand whatever is going on. Okay, let me take this coil. This is the coil. Okay. Let's suppose I bring another coil. Okay. And I'm going to set up current in this. There is a current, say I1, from this coil, in this coil. So this current will have a magnetic field. Okay, this will have a magnetic field. I'll use blue. So this will set up a magnetic field. Like that. Okay. So which way will it go? It's going like that. So magnetic field will be like this. Okay. Like that. So there is flux going into this coil because of this coil. So this is coil 1 and that is coil 2. This is, I call this is coil 1 and this is coil 2. Let us suppose I bring a magnet. Okay, I bring a magnet here. See, suppose I bring a magnet here, anyway, any other place, doesn't matter really. So I'll bring a magnet here. Okay, this is north, this is my south. Okay. So clearly, then field lines will go like that and come like that. Okay, and maybe like this. The field lines from the magnet. I've got that in black now. So you see, now it has two fields. The one field produced by this electromagnet, you can say, this coil, and another magnet, it's here. Okay. And what I'm going to do now is, I'm not going to stay put, I'm going to connect one more battery to this and then try to set up a current in this. Okay, I'll call this as current I2. So this current is flowing, its own current, and if its own current will also produce a magnetic field, right? So that would be, I'm using red to denote that. So again, like that. Okay? So this also points in this direction. You see, now this coil is impacted by all the three. It is impacted by the field in this coil and the field due to this magnet and also the field due to itself. There is a current flowing through it because of this battery and that will set up its own field. So the total field is a combination of all the three now. But the individual coil or even the individual element of the coil, the current element of the coil, you see, okay, we take this bit, small bit, it doesn't care where the magnetic field is coming from. It doesn't care. What is it going to do? It's going to say this: as long as there is a change in the magnetic flux through me, I'm going to generate an EMF. Okay? That's it. That's all it does. It doesn't care like where the flux is from. As long as there is change in magnetic field, there will be an EMF induced, and because there is an EMF induced, there will be a current flowing through it. That's all. If it's a closed loop, then current will be flowing through it. It doesn't care where this field is coming from, whether it is coming from here or its own self, doesn't care. So long as the flux through this coil is changing, then EMF will be induced. Done. You don't care about the source of the magnetic field. Okay? So, I want you to understand this. But it is for us to do the auditing job. Let's suppose that 5 volts are generated, because it's something, all these things are changing. Let's say 5 volts are generated in this. 5 volt is the EMF in that, the back EMF in that. Okay? Because these things are changing. Let's suppose it's not changing. Maybe you're wearing this battery or something, so you're changing the field, and you're moving the magnet here and there, thereby changing the field, the flux lines through this coil, and you can also be changing this voltage, this too. Then if you change that, then current that is flowing in this coil will also be changing. So you keep changing things. Now, because of all this change, let us suppose that an EMF of 5 volts is induced. Some EMF is induced. I am just assigning some random number to it. That's 5 volts. Out of this 5 volts, how much is due to this flux, its own flux, and how much is due to the flux from the coil, or how much is due to the change in flux from the magnet? And that auditing job is left to us. The coil doesn't care. The coil doesn't care. All it is going to say is, as long as there is a change in flux through me, I'm going to induce an EMF. That's it. I'm going to send a current. Okay? A back EMF. I'm going to change. I'm going to oppose the change. So to oppose the change, then I have to do something. So I will induce an EMF. That's what it will say. So this doesn't care, but it is for us to apportion which part of the EMF is due to this change, or that change, or its own change. That accounting is being done by us. Okay? So with that in mind, I'm going to do a simple, I'm going to take a simple case of just two coils and then derive an expression for that. So I'm going to take two coils. Okay? This is coil 1 and this is coil 2. So this has, let's see, current I1 flowing through this, and this has current I2 flowing through this. Okay. Let's say, I can vary this, I can also vary this. This is V1, V2, whatever, V1. Doesn't matter. So there are two coils connected to a battery, a varying battery, where if you have current flowing through this is I1 and this is I2. So what is going to happen is that this will set up a field. Yes, this is what we saw. So this will set up a field and use this color of field. So that will go here too. Something like this. Okay. So the field direction would be this, as we saw. Okay. So this is due to this coil. I will call this as phi, this flux totally. Okay, so phi into due to 1. Phi into due to 1. And this produces its own field. So because this is of I2, so then I'll say this is going to produce its own field, right? It's like that and like that. Okay, and this is actually phi. Okay, this is actually phi 1 1. The flux in 1 due to the current in 1 itself. So the total flux phi in 1, oh no, I'm sorry, this should be 2 okay? This should be 2. The flux in 2 due to current in 2. Okay? So this is flux in 2 due to current 1, which is in red. And what is in blue is flux in 2 due to current I2. Current in 2. Okay. So now flux into phi 2 can be given as the sum of both, right? Phi 2 1 plus phi 2 2. Okay. Then what's the flux linkage in this? The flux linkage in the coil 2 is n into d phi and n into phi 2. So that is equal to n into phi 2 1 plus n to phi 2 2. Okay. So now, what can we say in this? This can be written, okay, what is the EMF induced now? If suppose this flux is changing, phi 1 is, the current I1 is changing, I2 is also changing. So then there is the flux change, the total flux is changing. So which means what is the EMF induced in this then? The EMF induced in this coil is simply the rate of change of the flux, the total flux in the coil. So E is equal to minus n d phi 2 by dt. So that is EMF induced in 2. EMF induced in 2. So this is equal to this. And that will give you minus n d phi 21 by dt and minus n d phi 22 by dt. The rate of change of flux due to this, the rate of change of flux due to this one, this current. Okay? So, what do we know? N d phi 21 by dt is actually what? This is, what is this part? This N d phi 2 by d phi 21 by dt is the mutual inductance part, right? Because this is changing because of that. So you get minus M, the mutual inductance between these two, into, what is this? D I1 by dt. We saw that, okay? So this was proportional to the current in this, right? This flux was proportional to the current. This increases, this also increased. If this decreased, then this also decreased. So this was minus n d phi 21 by dt can be written as the mutual inductance M into d I1, the current in this, by dt. And this part can be written n d phi 22 by dt. That will be the self-inductance L into d I2 by dt. So that's your EMF induced in 2. Okay? This is the auditing job. We are saying out of the EMF E2 produced, this part has come from this change, and this part has come from this change, the current change in this. So this part has come from this current change, and this part has come from this current change. So this is how you put these things together. Suppose I bring in another magnet, then you need to account for that too. But then in that case, you wouldn't have an M or L, but you need to somehow find the flux from there. Okay, the change in flux from the magnet. But here it is easy for us to find M and L because the flux is produced by the current. So if you know the current, then you can do that. And when you have a magnet, then there's also flux changes, but then it's a little difficult to figure it out. But that is how we do it. If you want to bring another magnet here, then these two parts are fine, and you need to add one more part too. A flux change due to the magnet. But there is no current which is flowing in a bar magnet. So you need to go for the magnetic dipole moment of that magnet and do it slightly differently. Okay? But this is the simplest case where you have two coils. I1 and I2 are flowing through each of them. And because of I1, you will have flux. And because of I2, you will have flux here. If these two things change, then the flux in this coil changes. And if the flux in this coil changes, there will be an EMF induced. And what is the induced EMF? That would simply be the total flux change. But then you are apportioning it to the source. This is the EMF produced by this source. And this is the EMF produced by this source. And that auditing job, like an auditor, like a finance auditor, you do this auditing. Okay. Auditors do that. Okay. 100 rupees have come from this source, and another 200 rupees have come from another source. So they do that. They do those calculations. Okay. So the double entry accounting and all that helps in doing it. But let's not get into it. So like an auditor, you are doing it. Okay. If you have 300 rupees, you need to say 100 rupees has come from here and 200 rupees has come from there. That's exactly what you're doing here. Okay. But the coil doesn't care. Coil doesn't care about all your auditing. It is going to induce an EMF because the flux through it is changing. That's all. And it is for you to know what is doing what. That's what you do here. Hope this is clear to you. Now let's do problem 610, example problem. Obtain the expression for the magnetic energy stored in a solenoid in terms of magnetic field B, area A and length L of the solenoid. How does this magnetic energy compare with the electrostatic energy stored in a capacitor? That's the second part. Okay, so let's see. First, obtain the expression for the magnetic energy stored in a solenoid in terms of the magnetic field B, area A and length L of the solenoid. Okay, so let me take the solenoid. Long solenoid. What's B? Suppose I is the current flowing through this. Okay, you just saw that. I is the current flowing through this. And what's B? B is mu naught N into I. And the area, suppose if I look at the solenoid this way, you see it's going to be like this, right? I'm looking at the solenoid like this. This is a solenoid. This is how I draw. I'm looking at it like this. So this is the area of the solenoid, right? So this area through which the flux is now in this case coming out. Okay. So this is the area of the solenoid, and this will be the length of the solenoid again. So what is the energy stored in the magnetic field? We just saw that. We just derived that the work done, energy in the magnetic field is equal to the half L I squared. Okay. What is L? Which is self-inductance. What is L? L is equal to mu naught. And what we have? Mu naught into, we said like it depends on the geometry. Mu naught to N squared, and we said pi r squared into L. So pi r squared into, this is what we did, right? So now instead of pi r squared, I'm going to have the area simply. This is going to be A. This is my L. So this is my B, this is my L. And the work done, or the energy stored in it, because I told you that you need to do work to raise the current from 0 to value I, because as you increase the current, then it is opposing that change. The coil is opposing the change, so you are going to do work against it to put more and more current. Okay. So that is given by this expression. We just discussed that. Now I am going to take this and plug these things in. So what I am going to get now. So now W is equal to half into, instead of this one I am going to say L mu naught N squared A L, and then into I squared. Can I get I from here? I is, B is equal to mu naught Ni, so I will be B divided by mu naught N. So B divided by mu naught N, now this will be the whole square. Okay, so you got mu naught here. Okay, this is going to give me half mu naught N squared A L into B squared by mu naught squared N squared. N squared will cancel. then mu naught will go, and mu naught in the numerator will go, and mu naught in the denominator, mu naught squared in the denominator will become mu naught, and this is the expression you get. So the work done or the energy stored in this, in the magnetic field, is given by this expression. B squared AL by 2 mu naught. Okay. So what is AL? A is the area, L is the length. So it's like this. A is the area of the solenoid and L is the length of the solenoid. So that talks, it's equal to the volume of the solenoid. So this is actually the volume of the solenoid. Okay. So if I take energy stored per unit volume, what am I going to get? So energy, I'll say UB, energy stored per unit volume is going to be equal to the work done divided by the volume V, which is equal to work done by area into the length, and that is equal to B squared by 2 mu naught. Okay, so this is the expression for the total energy in this, total energy in the field. In the field. And this is the expression for UB equal to B squared by 2 mu naught. And this is the expression for energy per unit volume. Okay. So if you were to compare that with the energy per unit volume of a parallel plate capacitor, I hope you remember that U, this is B, magnetic field, UE, was half epsilon naught into E squared. This is joule per meter cube, and this was also joule per meter cube. So you can see that they compare like this is half B squared by mu naught, this is half epsilon into E squared. So you can see that the energy per unit volume is proportional to the square of the magnetic, square of the field strength. In this case, UB I can say is proportional to square of the magnetic field. And in this case, I can say energy per unit volume is proportional to the square of electric field strength. We did this for parallel plate capacitor, and we have done this for a solenoid. They seem like special cases, but that is not true. I mean, it's this will hold good for any shape, any capacitor of any shape, and a coil of any shape. So doesn't really matter. Even in free space in a particular volume, then this will still hold good, even without coils on plates. Okay. Anyway, so this is a comparison that we have done between energy per unit volume in the magnetic field and energy per unit volume in the electric field. So in both cases, the energy per unit volume is proportional to the square of the field strength. Hope this is clear to you.